In this video, I shall talk about the Meissner's effect. The Meissner's effect is an effect of the superconductor in which it expels all magnetic field from its body. So we can imagine, for example, starting with a superconducting body, say at room temperature, with magnetic field going through it. Okay, and then when this is cooled below the superconducting temperature and it becomes a superconductor, the magnetic field would be pushed out of the body. Like that. So this is the Meissner's effect. Room temperature, when it becomes a superconductor. Now, in order to explain this effect, we first start by thinking about the reason, at least an immediate reason, a first reason, why there would be no field in the body. If you look at the original body at room temperature, there's magnetic field going through it, and when it becomes superconducting, there is no more field inside. So first explanation to this would be that it is because the superconductor somehow produces an equal and opposite field inside itself, which cancels out the field from outside. So you have this external field, and then it produces its own field in the opposite direction that just cancels all the external field exactly. So this will be a first step in the explanation. And the next step would then be to ask why or how does this opposing field come about? Okay, but we know how a field might be produced because we know about electromagnets. So if we think in terms of an electromagnet, we could imagine that a field could be produced if there is a current going around the superconductor. So if I use the right hand thumb rule like that, then I would expect, I can imagine that if there is a current flowing around the superconductor, alright, inside the body of the superconductor like that, this current would then be able to produce that magnetic flux. Now that could be a second step in the explanation, but of course then we need to go on asking why might such an opposing current appear. Now from what we know in electromagnetism, there is actually a possible reason that we can think of, and that is the Faraday's law. Now we are familiar with Faraday's law in this form. If you think about, say, a coil of wire and a magnet moving towards it, then we know that this would induce a current in the coil, a current or voltage. So that's Faraday's law. Alright, well, if this part is connected up, then there would be a current. Okay, so we do know of this way, alright, whereby a changing field can produce a circulating current. So perhaps that field, that circulating current happens because of this external magnetic field, from what we know of Faraday's law. Unfortunately, this current would appear even if the external field is not changing. Alright, we could have started with the external field and a metal at room temperature, and if we cool it down without changing the magnetic field, the circulating current would still appear. Okay, so that's an important feature of the Meissner's effect. And because of this, we can't use Faraday's law, simply because the external field is not changing. So it wouldn't induce any circulating current that opposes it. So we have to find another explanation. And it is Fritz London, the German physicist, who supplied this explanation around the 1930s, I think. So his explanation is that within the body of a superconductor, the electrons, right? We think of electrons in a superconductor. His idea is to assume that all these electrons would form the same wave function that goes through the body, and they would form wave functions which are all the same and which are all in phase. In other words, the whole lot of the conduction electrons form a single giant wave function, or a macroscopic, right, a giant or macroscopic wave function. In other words, he imagined that all of the electrons go to the same state, like in a Bose-Einstein condensate, and they form the same wave function. Now at this point, you would want to ask, how is this even possible? Electrons can't all go to the same states because of the Pauli's exclusion principle. Now this is the point where we need to suspend our disbelief, as London and many other physicists did at the time, simply because by making this assumption that all electrons can indeed go to the same state to form a single wave function, London was actually able to explain Meissner's effect. What he did was to show that if there is such a single wave function, then when you have a magnetic field through this macroscopic wave function, the presence of the field alone, alright, doesn't have to be changing. Just by being there, the magnetic field would produce a circulating current. And because of this, the macroscopic function is able to explain the Meissner's effect very nicely, because this circulating field would then cancel the magnetic field from the outside, and therefore explains the observation of the Meissner's effect. Now, as to why all the electrons might go into the same state, that is something that has to wait another 20 or so years before the BCS theory and Cooper pairs were proposed. So this we shall look at in another video. So for now, we are going to follow in London's footstep. We're going to make this assumption, and then we are going to make this assumption, and we are going to derive the property that a circulating current is produced when you have a magnetic field in a wave function. Now, in order to do that, I shall start with Schrodinger's equation for a particle. Now, in Schrodinger's equation, if we have a single particle, say moving with a certain velocity v with a mass m in free space, just vacuum, then it can be described by this equation, minus I h bar d psi by dx equals to p psi. Okay, and we know what the solution for this is. Psi would have the form of e to the power of I kx. Right, and if we substitute this into here and simplify, we'll find that k is related to p by this, by h bar k. So this is what we know from quantum mechanics of a particle moving in a free space. Now, if we have a particle in a magnetic field, then we have to make some change to how we think about the P here or here. Now, when the particle is in free space with no magnetic field, the P is just mass times velocity, the momentum as we know it. But in the presence of a magnetic field, the P would here has to include the field, the electromagnetic field momentum, which is described by the vector potential A. So A here is the vector potential, which is related to the magnetic field by the curl of A. So with this, we can then write down the wave function in terms of the momentum and also related to the magnetic field, which is what we would need to explain Meissner's effects when the superconductor is in a magnetic field. So this connection means that we have to include the A, but the rest is the same. I can still use the same wave function. Alright, I already have it in terms of K, and now I simply add on the term for the vector potential to this equation for K. So we shall consider what to do with the with A afterwards. But for now, let's look at this wave function again and try to get to know it better. Okay, we can think of e to the ikx as cosine kx plus I sine kx. So the real and imaginary part. Now for each of this part, it would just look like a wave in one dimension, traveling in the x direction. Okay. Now what we want to do is to extend this idea, this idea and the equation to 3 dimensions. Okay. To explain the Meissner's effect, because we need to think about circulating current in 3D. So, in order to extend the idea to 3 dimensions, let's imagine a plane wave that looks like this in 3D. So instead of just one wave along one direction, we might have lots of this. Okay. So we have lots of these waves. So it forms something like perhaps a wave that you might see on water. Okay, and these are the wave fronts, right? The line joining all the crests. So with this picture, we might imagine extending this, generalizing this one-dimensional wave into 3D. Now that's one thing. The other thing is that the kx here describes the phase. So for example, when I move from one crest to another, one peak to another peak, the kx should change by 2 pi. Right? As we know, when the argument of the sine or the cosine goes through 2 pi, the sine function goes through one cycle. So in other words, the kx here describes the phase. Okay, so I can think of this kx, and that's a phase, which I'll represent that by the symbol phi. So when the argument changes by 2 pi, we have one wavelength in effect. So let's instead of thinking of kx as a separate k and a separate x, let's think about it as a phase. So now I shall write the wave function psi as e to the I phi. So now with this physical idea, let's relate phi to the vector potential. Okay. Right, and as you can see from here, phi depends on x. Now in free space, of course, these wavelengths do not change. Okay, it's like light going through free space. But in a field, it could be a magnetic field or an electric field, this wavelength can change, because we would have to include the potential, like vector potential or electric potential, into the Schrodinger's equation, and in general, when we solve it, it would not be e to the ikx anymore. Alright, and it would be a different wave function, but we can think of it as like e to the ikx, but with changing wave function. Alright, the spacing between the crests could change. So this means that we can think of the general case of this wave function as a field, in a field, in terms of a phase that in terms of a wave with different wavelengths. So that means that phi, instead of being just a linear function of x, all right, and which gives constant wavelength, I can think of phi as some general function of x. That means that it can depend on x in a more complicated way, so that phi can change by the 2 pi for one wavelength, sometimes for longer x and sometimes for a shorter distance of x. So that means I would think of this phi as a general function of x and not necessarily just kx, which is the case when I have a particle in a free space. So with this change in the idea, let's now substitute this expression into the Schrodinger's equation again. Now, so if I substitute psi into there, I will get, let's see, minus I h bar. Look at that equation there. I'm differentiating psi gives. Now I need to differentiate the exponential. That gives the same thing. But then I need to differentiate this argument, so that gives I times d phi by dx on the one side. And for p psi on the other side, I know that p should be mv plus qa. Let me write this as P times E to the I phi. I'll leave P as it is for now. So this is like the expression that I would get, and I can cancel this and this, and now I can put in the P from up there. Okay, now minus I times I is 1, so I get h bar d phi by dx on the one side. On the other side I get P, which is that. So that's mv minus plus qa. Okay, so now I have a relation between the phase, the velocity, and the vector potential. So let's continue from here. Now the next thing I want to do is that I want to imagine integrating this along a loop in 3D. So imagine that there's this 3D wave, and let me just think of, and this wave is represents the wave function that is inside the body of a superconductor. So within the superconductor, let me just pick any loop. Alright, just draw some random loop somewhere inside the superconductor going through the wave function. I'll call that L. Okay. Now, in a moment, you'll see why I want to do this. The first thing I want to do with this loop is I want to count how many wavelengths, or in other words, I want to find the change in phase as I go around the loop once. So it's like counting the number of wavelengths as I go around the loop once. Now if I have a simple plane wave like that, you can see that if I go around the loop once, say starting from any point and coming back to here, the number of wavelengths, or rather the change in the number of wavelengths, must be 0, because I might, for example, when I go from there to there, go through one wavelength, but when I go back, alright, going backwards means I decrease by one wavelength again. So if I'm looking, it's the same if I think in terms of phase change. I may increase by 2 pi when I reach there, but when I go back, it decreases by 2 pi again. So if there's a simple wave function like that, it is obvious that when I go around in any loop, the change in the phase should be 0. And this is the case where we would consider for the superconductor, we shall consider this simplest case, where it's just a simple wave going through the superconductor. Okay, the only way whereby we can get a non-zero phase change is if we have a circulating wave, and that means angular momentum and higher energy. Alright, so this simple wave is likely to be the lower or lowest energy state. So now, let's integrate this equation around the loop. Now clearly, we have seen that if we integrate, if I calculate the phase change around this loop, I must get 0. So if I integrate d phi by dx around the loop, now the x here is now generalized to this path around the loop rather than just a straight line in the x-axis. So that's how we would extend the idea of x, the x-axis. We would take the axis as being generalized into a loop like that. So if I integrate d phi by dx, I should get 0. Integrate around the loop. I should get 0 because there's no phase change. Now if I integrate these two, let's see what we get. Now because it's in 3D, I need to think of the v and the a as vectors. And when we integrate around a loop, we do v dot dl, where L is a short segment on the loop. And we have that as well. So QA dot dl. Okay, so we integrate that around the loop. So this is what we get. Okay. Now from this relation, we need to relate these to the currents that we would expect. Okay, the current which we would expect should be there in order to produce that opposing field that would cancel the external field. So to relate this V we will need to relate this V, meaning the V of the particles, to the currents. Let's say the current density J, and we would need also to relate the A there to the magnetic field, which which is present. Now, to relate V to the current density, let's recall what we know about electrons flowing, right, or charge Q, electrons flowing through a straight conductor. Now, if I have particles flowing through a straight conductor, I know that the current is given by the number density, meaning number of particles per unit volume, okay, multiplied by the cross-sectional area, multiplied by the velocity of the particles, and multiplied by the charge of the particle. So this is the results that we know from electricity. Now, using these results, I can find the current density, which is I over A, which is moving A over there, Q and V. Right, I'm going to use rho instead for the number density. So rho is the number of charged particles per unit volume. So using this connection between J and V, I can therefore write V in terms of J. So V therefore is equal to, moving those over, 1 over Q rho times J. So that we can use for this equation. So let me write down what we have so far. That equation, I shall now write it down as 0 equals to, there's the M there, and there is the over Q rho from there. Okay. And then we have the J, right, which will take the place of V. I still have this lot, this one, to deal with. Now what can we do with the A? Let's recall what we know about A. Now A is here, is the thing whose curl is B. Now but here we have it in the form of the integral over a loop. So what we need to do is to use the Stokes theorem to relate the two. Now according to the Stokes theorem, if I have an integral of a vector field over a loop, that is equal to, here we are, if you have an integral of a vector field over a loop, that's equal to the integral of the curl of the field over a surface bounded by the loop. Okay. And in this case, it's useful because if we look back at the curve of A, we know that it's the magnetic field. And this is nice because it gives, we now know how to relate the A dot dl in that equation, A dot dl to the magnetic field, which is just that. So that's the magnetic field. So now I know how to treat that. I would replace that by integral over S and replace that by the magnetic field dotted with the surface element. Okay. With this equation now, I've finally related the current to the magnetic field. Now let's simplify this equation, or rather let's write down a simpler equation for a simple example in which I have say a current circulating around in a body. It's just, for example, let's say I have a superconductor in the shape of a cylinder and I have this current going around it. And then I have this magnetic field from the outside, B. Okay, so for this simple example, I can write down a simpler form of this equation. Right, I would have, say for example, m over q rho, and then j and dl. Right, j would be constant around, say, a particular circle around the loop. So let's say I consider a loop on the outermost surface. So this length of this loop would be c, the circumference. So j dot dl becomes j times the full length of the loop, which is c. Okay, assuming that j is constant around it in this symmetrical case. And B dot ds is actually magnetic field times area, which is just the flux. Alright, integrated over S would be the total flux going through that surface. So that's the flux. And we have the Q. So finally we have our equation. Okay. Now this equation tells us something about the behavior or the physical behavior of the electrons in the superconductor when there is a magnetic flux. Now that's the external right. Not sure if you have seen this. Okay, just in case you have not seen it because it was too far down, let me quickly say this again. What I've done is that I have, from that equation, and for this example, I've said that when we integrate the constant current density around the loop, that integral becomes J times the length of the loop, which is C, and that is just the flux of the field going through the area enclosed, which is which I write down as phi for the B dot integrated B dot ds. So that's the flux. This is the external flux. Alright, and that's the current. The current density. Now let's think about the physical meaning of this relation. Now, see, we started from Schrodinger's equation, if you remember, earlier on. We have a Schrodinger's equation of a particle now here, Schrodinger's equation of a particle, and we have included the effect of the magnetic field. Okay. So when there is a magnetic, so what this shows is that in the presence of a magnetic field, we would get such a result. Okay, in the presence of this external magnetic flux, there would be a current. That's what this is actually telling us. Now think about the opposite case. If there is no magnetic field, then this must be zero, because if I have zero down here, this must be zero, since they have to add up to zero. But the moment that a magnetic field is present, okay, this equation tells us that this wave function must have a non-zero current. And this is the case. This would always be true, whether or not that magnetic field has been changing. Alright, so that means that we no longer need Faraday's law to produce the current. We no longer need a changing field to produce the current as we would expect from electromagnetism. According to quantum mechanics, as long as there's an external field coming into a wave function, the wave function would have to have a current going around inside itself. So what we have now, therefore, is an explanation for the Meissner's effect. And the explanation is that when there is an external field in a superconductor, the presence of the field produces a circulating current in the giant wave function made up by the electrons. And this circulating current then cancels off the magnetic field inside the body, and therefore you get zero field inside. So in effect, right, if you are just looking at the field around it, the effect is as if the superconductor has expelled the field from inside. Okay, so we'll stop here for this session.